Hi, everyone. Welcome to the first PyWhy Causality in Practice talk of the year. Uh, I would request you, if the speaker is speaking, maybe you can mute yourself. This will allow all of us to have good audio. Clark, maybe can you mute yourself?
Clark is already muted.
Okay. Thank you. Yeah, so welcome everyone. This is our first instance of the PyWhy Causality in Practice series. This is a talk series where we try to focus on causal ML advances in the research area, as well as how they can be useful in practice. I'm very delighted to have Professor Kun Zhang here with us because he's done some amazing foundational work in causal discovery. And at the same time, his team leads development of one of the most popular packages in PyWhy, which is called Causal Learn. So I'm excited so that Kun can share both his research experiences as well as give us some information, maybe even a short demo about the Causal Learn library. Kun, of course, has been working on causal discovery and causal inference for a long time. Currently, he's on leave from CMU and he's at the MBZUAI University. And he's done some work that I've been following for many years now. So I'm very glad that we are able to have him here for this talk. And with that, Kun, I would hand it over to you. Before that, I just want to make two quick housekeeping announcements. The first is, this is an open series. So at any point, if you have questions, you can just raise your hand. So Teams has a feature where you can see a hand on the top part of your screen. I will then look at those hand raises and just maybe interrupt Kun, and then you can unmute yourself and ask a question. The second thing is that this is a new series. We are looking for feedback on what kinds of talks you would like to have in the future. So I'll post a link to a Google survey in the chat, and we'd love your feedback on what kinds of talk you'd like to hear. And it'll also have the information about a Google group you can join or a Discord channel to get updated about new talks. So with that, over to you, Kun. I'm very excited.
Thank you. I don't. I see. So, can you see my video? Can you see my video?
Yeah, we can see it.
Okay. Because I'm using two devices, there's some kind of conflict. Great. Hello, everyone. So yeah, for most of you, good morning. So thank you very much, Amit and others, for organizing the talk series. And I think it's very important to bridge the gap between the kind of research, ongoing research in the causality space and the practitioners. So it's very exciting. And today I'm going to talk about the causal representation learning. Essentially, you can see it's a collection of developments and ideas in this particular kind of adventure. So you can see how we can try to learn the underlying causal representations, including latent variables and their relations for different purposes. So if you have any questions, just let me know. I think it's nice to make the talk interactive. Okay, so I'll briefly go through a number of ideas. I don't think it's possible to really talk about detail of any particular development, but I'll try to give the view regarding where we started and what our final goal is, and how we could just achieve that step by step. So let me just start with some motivating examples. So here, I guess you are familiar with the examples, right? In the first example, you can see in order to change lung cancer, let's say incidence of lung cancer, you have to use the causes instead of the variables that are just dependent on the target variable. And then in the second example, known as the Simpson paradox, so in this particular example, in order to really improve the recovery rate, right, or to find a good way to treat the patient, we care about not just associational information, but just causal influence or the property of the particular causal link. Here, you just care about the influence from treatment to recovery. And this influence can be totally different from the dependence pattern between them because of the existence of other confounding variables, right? So this is the message we can learn from symptom paradox. In the last example, you can see basically, if you consider only college students, say 60 years ago, female students were smarter than male students on average. Why? Because essentially, see, we are considering college students. It's a selection problem. But selection problem or selection process is also part of a causal process, right? So when we try to understand why things are dependent, you may have to figure out actually it's a selection, right? And particularly if you try to go from the selected sample to the population, then clearly you have to identify and make use of how the selection process happened. Okay, so now let's look at another example. So this is a kind of well-known cut-pull problem, right? It's a simulated environment for reinforcement learning. And here we would like to keep the inverted pendulum balanced. So suppose now you have no idea about the background knowledge. You don't have any kind of, you don't have any understanding of the mechanism right here. This is the first day I'm basically living in this world, and I just see the picture or video. Right now, suppose you just want to keep the inverted pendulum at the bottom balanced. You only pay attention to this one. And now you can see you just see video data. How can you really figure out what action, what we can change to achieve our goal, right? So in this problem, clearly you try to have a causal understanding of the unstructured data, say video. And then you try to make use of the gain causal understanding to see what changes you can apply to the system to achieve your goal, right? So in this case, you can see this is suppose this video we have. Now you try to figure out what we can do. Clearly, causal representation would be very helpful. And at the bottom, you can see the different kinds of state representations we can learn from this data set. So on the very left is the reward relevant. Right here, I should play a video. You can see you care about the pivot position right here. And in the middle, this is the controllable but not reward relevant. Here, basically, you can control the color of the light, but it is not relevant to the reward, and so on. So you would like to relearn the underlying representations so that you can see what you can do to achieve your goal. So this is also related to disentangled representation learning, right? And actually, we gave disentangled representation learning the following definition. Why? Because some people may understand disentanglement in different ways. So essentially, when you have disentangled representations, you try to make sure each of those disentangled representations or variables manipulable in the kind of separately, right? At least potentially. So what does it mean? It means that those disentangled variables or representations or factors should be involved in the causal process so that we can really have a way to change or manipulate each of them, at least potentially. So now you can see from this perspective, disentangled representation learning is nothing but a causal representation learning, because you have to make sure that those learned representations are part of the underlying true causal process so that you can manipulate each of those things separately. Okay, so now we can consider other problems in machine learning, AI. You may consider domain generalization, domain adaptation, clearly for decision making. You already saw example. It's better to have a causal understanding of the environment and then make use of it to foresee the consequences of different actions and figure out what optimal action you can take. And for fairness, right? Essentially, fairness is not associational condition. Instead, fairness is the state you want to achieve, right? So in order to achieve the state, clearly you have to discover and make use of the causal, the process of the causal, the information of the causal process. And in generative AI, similarly, you may want to learn the concepts and what the concept mean, and then can try to generate something new, right? And similarly for recommendations, you can see clearly recommendations are given because of the particular purposes, and the particular properties of the causal process, right? So maybe we, in the future, we can make recommendation systems really transparent, right? So we can ask them to provide, to make it very clear what their purpose is and how they can make use of our kind of reaction patterns. Okay, so at the bottom, you can see another example is the adversarial attack problem. Basically, we know the problem. How can we really deal with the problem? Mathematically, you can show that as long as machines and human beings learn and make use of different kinds of high-level representations, we may always have this kind of adversarial vulnerability problem. Then how can we solve the problem? We have to understand what kind of representation we make use of, and then find a way so that machines can learn something consistent, right? So generally speaking, we try to learn generative features or causal features to explain the external world, right? This way we can connect different scenarios and gain understanding of the world and see what we can do and so on. So basically, we try to learn such features. Then we need to find a way to find the principles that are technically operational so that the machines can also learn those feature representations. Of course, the machine may learn kind of more, right? More information, but basically they should be consistent with what we make use of in order to avoid this fundamental adversarial vulnerability problem. Okay, so here you can see very brief history of causal discovery. And here by causal discovery, I mean the task of finding the underlying causal structure or causal model from observational data. So Clark Glimmer is here, but Clark Glimmer is familiar with each story in the history, and actually he's a pioneer of causal discovery. I'll mention name later. So here you can see Reichenbach's the common causal principle, but explained in his book, Direction Time, is basically in spirit, is very similar to the idea we make use of for causal discovery. And then K-very formulated Markov condition. And then in 1993, the book Causation Prediction Search was published by Peter Svertis, Clark Glimmer, and Richard Shines. So basically in this book, you can see causal discovery was made possible. And it's also formulated the faithfulness condition, provided a PC algorithm, Peter Clark algorithm, SGS, Spertis, Glimmer, Shines, algorithm, FCI, and so on. So basically, this is the classical book in causal discovery. And sorry, in 2000, Prof published the book Causality, Modeled Reasoning and Inference. Basically, this book makes a lot of concepts very clear and is mainly focused on causal inference or identification of causal effects. And in 2003, Chikrin published a paper on greedy equivalence search, which is a very popular one. And later, people developed a functional causal model-based methods. And by functional causal model, I mean you have to make additional assumptions on the causal mechanism. And then you can gain kind of a better identifiability of the causal structure. And recently, and actually not recently, more than 100 years ago, you can see fact analysis formulated by Spearman aimed to discover latent variables under some conditions. And the conditions were made kind of much more general in the last decades. So basically, the tetradic condition was used for discover latent variables and their relations, and also proposed the latent how to estimate the latent tree structure in SME Ricardo Silva, Richard Shines, Clark Glimmer, and Peter Spertis formulated the measurement model and proposed a method to estimate the measurement model. And later, we also developed the gene condition, generalized independent condition, and modified the rank deficiency condition to discover and discover latent variables together with their relations. So this is a very kind of brief history of the causal discovery literature. Now, let's see why it's possible to discover causality from observational data. So first of all, we know in order to, it's an inverse problem, right? In order to say something about the hidden causal world, we have to, first of all, we have to figure out what kind of properties or what kind of information of the causal process is reflected in the data, right? So, and then we can try to see whether by making use of that piece of information, whether the underlying structural information can be recovered. So the first one basically is related to the so-called modularity property, or sometimes it's also called exogeneity or independent causal mechanism. Essentially, when we say here, we have a causal process involving rain, wet ground, slippery. Although all the variables can be dependent, this system can be divided into several separate systems. And here you can see we have one process to generate rain, the second process to generate wet ground, and the third one to generate slippery from wet ground. Although variables can be dependent, those modules are clearly kind of irrelevant to each other. So if you change one, others will not change for that reason. So based on this property, we can formulate conditional independent relations among the variables. And the conditional independent relations can be used to recover causal information up to the equivalent class as used by PC and FCI. And we also have the independent noise condition because noise is just some omitted factor involved in a particular process to generate one variable from its parents. Then this variable should be independent from the input, the cause. And similarly, we also have the minimal change principle of the causal representation across different environments, so in non-stationary environments. And if they change at the same time, they should change independently. All those conditions can be used to recover some information of the causality. So those things can be seen as a kind of information that the causality leaves as a footprint in the data. The second problem is whether we can make use of the footprint to really recover the underlying true causal structure or causal model. So this is the identifiability issue. Basically, here you can see in all those methods we have identifiability, meaning that if you have enough data following the assumption, then you can just converge, the algorithm can converge to the true causal structure, right, or causal model. Okay, now let's have a look at the causal representation learning or causal discovery problem. I don't really distinguish between causal discovery and causal representation learning in a very careful way. Why? Because both of them try to recover the underlying true causal process, while causal representation learning focuses more on the high-level latent variables. For instance, if you have image pixels, right, they are dependent, but there shouldn't be direct causal relations between the pixels. Instead, they may be generated by some high-level concepts, right? So causal representation learning is more about how you can recover those latent variables, while causal discovery, by definition, aims to recover everything in the causal structure, right? So, okay, so here, in order to go further, we might consider 3 dimensions or axes of the problem. The first one is what kind of data you have. You may have i.i.d. data, or you may have non-i.i.d. data. Causality is basically about the changes, right? We understand the causality in order to apply optimal interventions, for instance. At the same time, if there are changes, then it's easier, right, to discover causality because you have more distributions. So the first one is whether I have i.i.d. data. The second one is whether we can benefit from some assumed parametric constraints. In some cases, we may have linear model, right? And then the search space is much smaller. But in some cases, we may not have such parametric constraints. And the last axis is whether we can allow a lot of latent confounders, right? So for the purpose of causal representation learning, clearly we should allow latent variables because basically causal representation learning focuses on confounders or latent variables. Generally speaking, if you don't have strong knowledge about the system, we should allow latent confounders, right? And try to see how they are related to what we see. And here, by latent confounders, maybe a better way is to put it this way. So they actually exist in the system. Unfortunately, we cannot measure them, right? But they are just there in the system. So we try to infer the information of the variables. And then after that, we can just say something about latent variables, or maybe as time goes on, we can have better tools to measure the variables, then you can measure and make use of them, or even manipulate them. Okay, so here you can see a summary of the recent advances in causal representation learning. Now you can see the 3 axes, including whether the i.i.d. data, whether we can benefit from parametric constraints, and whether we allow latent confounders. And on the very right, you can see what we can get. Essentially, is about what you can really recover from such data, right, under the assumptions. Very oftentimes, especially in the i.i.d case, we can only recover the structure up to, say, equivalence class. We may have different kinds of equivalent classes, but usually that's the case. But if you are willing to make some other assumptions, say parametric assumptions, generally speaking, you may be able to recover the underlying DAG or even directed cyclic graphs uniquely. And similarly, in the non-i.i.d case, generally speaking, causal discovery or
I think you muted yourself accidentally. Still no sound.
Wait. Can you hear us, Kun? Kun, we can't hear you. You'll have to unmute yourself.
Oh, yes, I don't. Yeah, that's very sorry, very strange. When did it happen?
Now you can hear me,
right? Yeah, 2 to 3 minutes, maybe.
Oh, okay. I'm very sorry. Okay, so let me continue. Basically, it's a summary. It's very natural, right? If everything is non-parametric and you allow latent compounders, then usually you can only have the equivalence class. But if you have additional information, such as temporal information or multi-distributions, then you can improve the identifiability. Or alternatively, even in the i.i.d case, if you are willing to make some assumptions on the mechanism, right, then usually you can just improve the identifiability. And you may even enjoy the unique identifiability of the underlying structure. Okay, so now you can hear me fine, right? Amit?
Yes.
Yes, we can.
Okay, yeah, okay. So now let me just give a couple of examples to illustrate the ideas. So this is the first example. The data set was collected by a friend of mine, Marin Novak. So she would like to, in archaeology, they try to understand why we look different, right? We are from different areas and we look different. So she collected those variables, 8 variables, in 215 skeletons. Basically, she measured the values for those variables, including sex, cranial size, geographical location, climate, diet, and so on. So basically here you can see different variables may have different dimensionalities, and the relation can be linear or nonlinear. We have no idea. In this case, it's natural to make use of just the conditional independent relations. So now let's have a look at the conditional independence-based method. Basically, we just make use of conditional independent constraints to recover information of causal structure. So typical algorithms include PC and FCI. This is how it works. We have data on the left, and from data you can discover a set of independence or conditional independent constraints, and then you try to find a DAG or set of DAGs known as equivalence class to satisfy those constraints. So on the right, you can see since 1 and 5 are independent given 3, there are no link in between. There are no direct interaction between the two variables, and so on. And then we can get the, this is right here, you can see we can discover, we can determine the direction between X2 and X3, and between X3 and X4. This is a V structure, but we cannot go, we can also do orientation propagation, but we cannot determine the direction between 1 and 2. Later, you can see if you assume the system is the linear and Gaussian, then you can just recover all the orientation information. Okay, so right here, you can see the result of applying the PC algorithm together with the kernel-based conditional test to the data. Now everything is transparent, so it's amazing. Now you can really see our geo distance from Africa, a particular place in Africa, is root cause. It causes the climate and the cranial shape differentiation and so on. So now, given a color picture, which actually distinguishes between direct causal inferences and indirect causal inferences, we can really see how to achieve our goal by making proper changes for which we have just pay a minimal price, right? So you have the freedom to do that. Okay, and then now let's assume something about the mechanism. Right here, first you can have a look at the linear non-Gaussian model. Right here, the causal information or causal influence is linear, but the noise terms or the causes are not necessarily Gaussian. Actually, at most one of them is Gaussian. And then you can immediately recover the causal direction and hence the causal structure from data. This is very nice, and this is also related to a widely used technique called ICA, independent component analysis. And amazingly, you can see even if the function is nonlinear, the same thing still holds true. In the post-nonlinear model, where you have two nonlinear functions, generally speaking, you can say that only in the right causal direction you can you find the independent noise term. Otherwise, if the direction is wrong, then the recovered residual E cannot be independent from the hypothetical cause. The same thing holds true for additive noise model. So that's very good. If you have some information, make use of it, you can greatly improve the identifiability of the causal structure. And here you can see an example. Basically, on the top, you can see the data, the scatter plot of data. For if you assume X1 causes X2 fit a model, you can see the recovered residual is independent from X1, the asymptotic cause, but in the reverse direction or in the other direction, that's not the case. Then we can say we would prefer the causal direction from X1 to X2 according to this model. Okay, now let's look at some new problems. Right here, you can see the data set. This is the data set we just analyzed half a year ago. This is personality data. You know, each of us try to understand our personality, right? We try to see how we are different and how to improve a particular dimension of our personality. How can we achieve so? We cannot really see or touch the personality. Instead, we can only say design questionnaires and provide our answer scores and then try to look into the hidden world. Right here on the right, you can see there are 50 questions, right? E1 is the first question designed for the E extroversion dimension of personality. So here, they designed the 50 questions in order to assess the big 5 personality traits. Good, now we can just analyze the rating scores or answer scores, and we try to see the underlying causal process from them. In other words, here we analyze observational data corresponding to xi, but we believe that they are generated from latent variables, which are also causally related. The problem is how you can really recover all those latent variables and relations from observational data. Okay, so I'm going to give some examples. So in the linear Gaussian case and also linear non-Gaussian case, and we also have some results in the general nonlinear case. I will say a few words about it because they are technically more challenging. Okay, so first of all, here you can see by making use of rank deficiency constraints on the cross-covariance matrix, we can actually discover information of the latent variables, right? So we just make use of covariance matrix of all the variables, and then we just pay attention to different parts of the covariance matrix, and then we check for rank deficiency condition, and then you can just say something about the latent variables. Why? Here, let's consider a particular example. Suppose we consider the cross-covariance matrix between XA and XB. Sorry, I cannot make annotation. So XA and XB. Here, XA is the set of variables X10 and 11, right here in the red box. And XB is basically a set of all the remaining variables. Now, you have the cross-covariance matrix. What's the rank of this cross-covariance matrix? Actually, its rank is just 1. Why? Because you can see X10 and X11 are related to all the remaining variables via a single latent variable. And you can show that in this case, the rank of the cross-covariance matrix would be 1. Good. Now, this means the rank of the cross-covariance matrix can tell us something about the existence of a bottleneck representation or latent variable, right, between the two sets of variables. This is the basic idea, and then with some kind of tricks, you can recover right here the equivalence class of this DAG at the bottom without any difficulty. Okay, so now we can go further. In this graph, you can see we don't have causal influences from measured variables to latent variables, LIs, right? We always have causal influences going from the latent variable to the measured variables. That's not really flexible. In practice, you may have environmental factor, right? Then environmental factors may be causes of latent variables. So recently, we just made it completely flexible. We just consider partially observed linear systems. Right here, you can allow causal influences from latent variable to measured variables, between latent variables, between measured variables, from measured variable to latent variables, and so on. But eventually, you can still recover the structure up to some equivalent class by making use of a well-designed rank deficiency condition. And it's interesting to see that, in fact, even the partial correlation test at a particular condition implement test is a special case of the rank deficiency condition. For instance, here, suppose the rank of the two cross-correlation measure of the two sets of variables is 1, and here the two sets of measured variables overlap, right? X2 is shared. Right here, one set of variables is X1, 2, the other is 2, 3. X2 is shared. And if the rank of this cross-correlation matrix is 1, what does it mean? It means that actually one variable can just separate the two sets. X2 is shared. So this is equivalent to the statement that X1 and X3 are conditionally independent given X2. So this is nice because you can see a very general condition you can verify from data to discover the underlying causal information. And the paper was just accepted. Oh, this is ICLR, sorry, the typo. Okay, so this is the result we obtained on the personality data. Right here, OI correspond to the questions designed to assess the openness dimension. And all the LIs are latent variables. The method automatically discovered from data. Let's just pay attention to one cluster. On the very left, you can see we have L4, L5, and L6 discovered from data. In fact, they correspond to imagination, understanding, and creativity. And at the same time, you can see the causal influences that go from L4 and L6 to L5. Now this is interesting because you can see imagination and understanding are both causes of creativity, right? So all those things can be discovered from data. Right now, we are analyzing a data set with 300 questions, and a lot of interpretations are so interesting. Basically, you can really see a subtle way to change particular dimensions of our personality by understanding ourselves through methods. Okay, in the linear non-Gaussian case, we have more information. Why? Because right, with non-Gaussian data or non-Gaussian variables, you have higher order statistical information to make use of, in addition to the covariance information. So in this work, we just provide the necessary and sufficient conditions on the graph so that it's identifiable, but we don't have a practical method. And later, we develop a gene condition, generalized independent condition. And with this condition, by testing whether combinations of the measured variables, only measured variables, are independent, you can verify the existence of latent variables, figure out where they are, and furthermore, discover the causal orders of the latent variables. Okay, I'll skip the detail. So first, you can find the causal clusters. By a cluster, I mean a set of variables, a set of measured variables sharing the same latent variables. And then you can just discover the causal order or causal structure of the latent variables. So here you can see application. This is the application to the teacher's burnout data with 28 measured variables. We automatically discover all those hidden variables. And it's amazing that the method, the result produced by the method is almost identical to the hypothesized model produced by experts. So this means two things. First of all, the expert knowledge is very good because knowledge can really explain the data. Second of all, computational methods are very useful for the purpose of discovering causality. Okay, so basically you can view rank division condition and the gene condition as particular types of sparsity constraints, right? In some way. In fact, even in the general nonlinear cases, the same thing holds true. We can benefit from sparsity to discover the underlying true latent variables. And this is the work done by Yujia, who is here. Basically, under condition that for each latent variable Si, there exists a set of observed variables such that the intersection of their parents is just that variable, Si. Then the latent variables are identifiable. So you can just recover those latent variables up to component-wise transformation. For instance, here, the condition holds true. For S1, the first latent variable, you can see it has two children, X1 and X2, X1 and X4, and the intersection of their parent sets is just S1. So this condition holds true. And then you can just recover the structure and you can estimate the underlying latent variables relatively uniquely. I'll skip this part so we can do first the generalization to make it more practical. And so I should finish everything within minutes. Otherwise, Yujia will talk about the causal learning for about 10 minutes. Okay, so you just saw some examples in the i.i.d case. Now let's go from the i.i.d case to non-i.i.d case. First, let's just violate the first I. Now we have temporal data or time series data. We have it's not independently distributed. Okay, so this is a particular type of work we just did. On the left, you can see high dimensional time series X. They are assumed to be invertible transformation, arbitrary transformation of the underlying true causal processes. And for the underlying true causal processes, there are only time-delayed causal relations. There are no instantaneous influence, right? So if you have high resolution data like video data, the causal, it takes time for causal influence to take place. Then you can just assume that they are the only time-delayed causal relation. And then you can show that even if everything is non-parametric, under relatively mild assumptions, the model is identifiable. All the latent processes can be recovered up to the component-wise transformation. Here you can see one example. So here you can see the data set. There are 5 balls with different colors. Between some of the balls, there's a hidden spring. Okay, just with this video data set as input, we discovered 10 latent variables. They turn out to be the X and Y coordinates of the 5 balls. So you can really see the underlying kind of representation, meaningful representations together with their relations. Okay. And this idea can also be applied to reinforcement learning. You know, in deep reinforcement learning, we should try to improve the interpretability and the generalization ability, right? At the same time, we should try to find a way to deal with the issue that usually the problem is the data hungry, right? So what can we do? We can just learn good representations. Specifically, we can divide all the meaningful static representation into 4 categories, depending on whether they are controllable and whether they are reward relevant. So here you can see a graphical characterization of those 4 categories. And then we show the identifiability of each of those 4 representations in each of those 4 categories. And I will skip the experiment results. Basically, here you can see the confusion matrix. All the true latent variables in the simulated environment can be perfectly recovered from observational data, from video data. Okay, and with the learned reward relevant representation, you can see we can just learn the optimal policy faster, as you can see from the blue curve. Good. So now let's see what we can benefit from multi-distributions. So if you have non-stationary data or heterogeneous data, you have multiple distributions, then what can we do? We know causality or causal modeling and the distribution shift are heavily coupled. If you know causal model, you know a certain type of change can happen, but there's a modularity condition, right? So they change independently, different modules change independently, and so on. That means if you really see the phenomenon of distribution shift, you can just quickly verify which causal model would be plausible. Okay, so here the causal influences can be stronger, weaker, or some causal influence can even vanish. And here we did this a couple of years ago. Basically, you can discover for which variables the causal mechanism change. And after that, you can discover causal directions by making use of independent chain property. And for the changing causal mechanisms, you can even try to find a low-dimensional representation for visualization. This way, you can understand how and why a particular causal mechanism changes. Okay, now this part, maybe I should skip this part. This is about how you can make use of the representation for domain adaptation. I should skip this part because otherwise we are already running late. So, but let me say a few words about this problem. This is known as unsupervised image-to-image translation. So you have a lot of pictures taken in the summer, and also you have a lot of photos in the winter. Now they are unpaired, but you try to find a transformation so that for any given image in the summer, you can find a counterpart, right? A proper counterpart in the winter. So this problem clearly is ill-posed. Why? Because we only have the two separate data sets or two separate marginal distributions, but we try to establish the connection or information of the joint distribution, right? This problem is ill-posed and it's also very hard. However, by formulating and making use of some minimal changing principle right here, we can have unique solution in this case. Okay, and here by minimal changing, I mean the following thing. We just try to explain the difference across the data sets by making use of a minimal number of changing components or factors corresponding to the style. Image is generated from content style. We try to have a minimal representation of style to account for the change across domains. And this way you have identifiability. And then you also see the correspondence information across data sets. And here you can see some results. Basically, this is the data generation problem, which is very similar to a translation problem. You have, in this particular example, you have two separate data sets corresponding to the male and the female without the correspondence information, right? And then we are asked to generate two pictures with the same content, but different genders. And on the left, you can see the result given by our method. They are essentially kind of almost identical, apart from, except for the gender in some way. But other methods, you can see the result given by other methods. There's some kind of spurious change right there. Okay, so summarize, a lot of tasks involve suitable representations, and the causal representations seem to be to serve as a kind of foundational thing to solve a lot of problems. In some way, if you really have the causal representation, it's a kind of foundation model you can make use of, right, to deal with a lot of downstream tasks. And the second point is that the causal representations or causal structure involving latent variables can be recovered up to some pretty strong indeterminacies under appropriate assumptions. First of all, we have to formulate causal principles and make them technically operational. And the second issue is to establish identifiability guarantees. Without the identifiability guarantees, you may just end up with some good results by accident, but there are no guarantee to say that, yes, they are consistent with the underlying true causal process. And generally speaking, if you have non-i.i.d data, strong identifiability results can be established. Why? Because you have more information. And in the i.i.d case, usually you can benefit from parametric constraints or sparsity constraints. Okay, thank you very much. Amit, sorry, I'm running late.
No problem. I think this was very useful. I especially appreciated the overview you gave us right from 1990s to what's happening today. Maybe we can take a few questions before we move on to causal learn. So I think there's a question from Clark. Go ahead.
Hey, Clark. I think you are muted.
Now, can you hear me?
Yes.
I have two questions. One question is kind of hard to answer. So we have a really powerful array of methods for analyzing non-experimental data. those methods, if used, would revolutionize the results in several sciences, mostly human sciences, psychology, epidemiology, economics, etc. But they are rarely used, at least by professionals in those areas. How come?
Should I answer this question first, or should I wait for another second question?
No, first question.
Okay, so we discussed this. I mean, great question. I think here a lot of people thought about this question. So first of all, you can see the trend. You can see more and more people actually are use to such ways to deal with the data, right? And they are more and more people are using the method to analyze their data. You can see that, right? A lot of biologists contact you. They are interested, and they can also produce very exciting results. So this is one thing. The change is happening. Second, we are not there yet. So you can see one day, if we say, yeah, causal discovery or causal representation learning is a standard tool you can make use of, right? There's a long way to go. Because right now, if you want to deal with real data, there are so many factors to consider. And that's why you can see we have to allow latent confounders, measurement error, and so on. And right now, we are still trying to deal with each of those practical issues without an automated kind of unified platform. I think at some point, we can develop a unified platform so that the users can just basically apply, just load their data, click some buttons, and then get some results with interpretations. If that happens, then I believe a lot of, say, social scientists, biologists will basically use the causal discovery methods very naturally. But we are not there yet. And this is one of the sentences I shared some time ago in the panel. So if we are excited by the success of particular applications, right? We are not there yet. One day, we will be very disappointed by a single failure case. Then we can say, yes, causal discovery is really reliable. Clark, are we on the same page?
Yes. Now my second question. So the history of science shows a lot of causal discovery by this kind of procedure, not the one you're describing. That is to say, if I look at the history of thermodynamics, if I look at the history of gravitational theory, electrodynamics, they share this pattern. Empirical regularities are found, generally several of them. And from those empirical regularities, not from the individual data points, a theory is constructed. Do you have any ideas about how to automate that sort of method?
Wonderful. Yes, actually, we also touched on I briefly discussed this issue with others. So eventually, a lot of people are doing kind of foundation model and so on. But to me, it's so important to really bring something new or to increase human knowledge by developing a system like great scientists. By that, I mean the following thing. Essentially, you are trying to discover the latent variables, right, in the universe together with the laws of representation and relations. And I believe now the ideas of causal discovery and causal representation learning can naturally inspire an automated way to do AI for science. And you can just discover those, say, entities, laws automatically, and follow the same, clearly they follow the same spirit, right?
I hope.
Yeah, so let's work on it. I believe pretty soon we will have a system that can do it.
Thank you.
Is that answer? Okay, thank you.
Dimitar, you want to go next?
Yes, I have a question which is related to what already Clark Lymore asked, which is how to popularize, how to make these methods more accepted in the community. And I know that I heard that Zhang said that reinforcement learning is also will benefit from application of these methods. I think that would be a great vehicle because reinforcement learning right now is applied to a wide variety of tasks. And if you can make these causal or counterfactual algorithms be beneficial for some more complex reinforcement learning algorithm, this will definitely shed a lot of light to those algorithms.
Wonderful, thank you. I completely agree. And at the same time, in my response to Clark's question, I omitted one point. So in specific problems, right, the assumptions are pretty clear and also property of the data are pretty clear. So we have some guarantees. I mean, in some specific domains where we have strong knowledge, we can just convince them to apply specific causal discovery method. And the second point about the reinforcement learning, I completely agree. And I think basically they can mutually, the benefit is mutual. So reinforcement learning and causal representation learning can benefit from each other. You mentioned how reinforcement learning can benefit from causal representations. And on the other hand, you can see reinforcement learning or some kind of active learning is so essential if you try to learn the causal representation of the environment quickly. So this part is also very important. And I think this involves how you can define curiosity and a lot of other things. And I believe this will be a kind of very important research direction in the relatively near future. So is that a proper response to the point?
Yes, yes. I would like to see actually more papers. If some such papers can be published in appropriate place, I would like to see more papers of application of causality and related causal algorithms in reinforcement learning.
Yeah, wonderful. Actually, that's one of the ideas behind causal representation learning for societal decision making. You know, we are involved in the AI Institute on societal decision making, and we are doing causality for that purpose, right? Exactly as you just mentioned, you have to find a causal model, and then you can do counterfactual inference, or you can foresee the consequences of different interventions and so on. And at the same time, some people started working on how to basically learn causal representation in a continual way or lifelong learning way. And this will involve what kind of information you can collect and what kind of change you may want to make. This is naturally a part of reinforcement learning. Thank you. Oh,
Luigi, go ahead.
Yeah, thank you. So as a traditional scientist, I understand how we estimate the causality through randomized experiments. So I see specifically one of your example, the archaeology. I remember you assume that is i.i.d. data. So I'm just curious, how did you like make this assumption? Is it by like domain experts, or is there any specific techniques we can use?
Oh, okay. Wonderful. Yeah, right here, as you can see in this, you were talking about this data set, right?
Yes.
In archaeology. Yes. So here you can see we only have a single data set, right? Data points basically, and we have no idea about the heterogeneity or anything. So it's we can only consider this as i.i.d. data. And so of course, in this case, the information or constraints you may make use of would be relatively weak, since you don't have additional constraints, but still, by making use of just condition independent relations, you can discover very strong information. And furthermore, very oftentimes the problem can be clearly more complex. This problem is, I would say, when they measured those 8 variables, they already made use of their background information, right? As a consequence, you can see very nice graphical representation. Otherwise, there could be a lot of latent variables, right? Relations can be very messy. So eventually, I think, even if that's the case, with the suitable causal representation learning techniques, domain experts, I mean, like you, scientists can still benefit from it because the learned representation can help you formulate a lot of hypotheses and tell you which omitted variables should be important and where to try to find them. So, I mean, we should, machine learning people, especially causal scientists and other scientists in specific in sciences, in different disciplines of science, should kind of work together to really make that, I would say, to make scientific discovery kind of smoother in some way. Yeah, I think we are on the same page, right?
Yeah. So I just feel it's so difficult to make that assumption. The data is i.i.d, and you know.
Okay, what do you mean by i.i.d? So basically, you here by i.i.d we mean the following thing: it's independent and identical distributed data. We have a single distribution. Even if you have, say, 3 data sets or 3 distributions, right, which are different, but now if you mix them, you are going to have a mixture distribution, and then you can still consider sample as i.i.d draws from this mixture distribution. So in this case, I don't know how strong. I don't see how strong the i.i.d assumption is. Instead, I consider i.i.d assumption as something, in this scenario, as something relatively weak. Because if it's not i.i.d, then you may have multiple distributions, right? Or some temporal or geographical connection information. Those things would be harder to obtain and stronger. What do you think?
Because you know, I feel the scientific discovery is trying to identify something, well, you know, unknown, and if we make assumption that they are i.i.d, and we might lose the opportunity to find something really important, and the result of that might be kind of misleading. So that is what kind of I'm afraid of, you know.
I see. That's very fair. I completely agree. That's why basically I said the i.i.d assumption itself is not strong. Instead, if you have additional information, you should make use of it. For instance, if you know, oh, actually the data set can be divided into 2 subsets with different distributions, you should make use of it. If you know there's some temporal information in some scenarios, you should make use of it. So that's why if you drop those things, you just have a single data set, you can say, oh, I just have sampled from a single distribution. But still, even in this case, with very weak input, you can still get something. So I think, yeah, your point is that, yeah, if you just assume it's i.i.d, some information is lost, right? We completely agree. And at the same time, you can see, even if some important information may be lost, you can still recover something about the causality.
I see. Gotcha. Thank you.
Thank you.
Hey, Kun, we're on time. I have a suggestion. Maybe we have the tutorial on causal learn in a different talk, maybe the next talk. Perhaps you or Yujia could give it.
Yes, that would, from my perspective, is a good idea, because today, I didn't really give many examples. Maybe Yujia, you can present causal learn together with concrete examples. That will take longer, but that can make things really clearer. Yujia is here. Yujia, what do you think?
Oh, yeah, sure. I think it's a good idea. Yeah.
Okay, so Yujia, I'll follow up with you tentatively for the next slot. You can present causal learn, and yeah, we'll figure out the logistics.
Yeah, okay.
Cool. Kun, thank you so much. As always, I think your talk was very useful. And I think the questions themselves are very thought-provoking. So I really enjoyed the discussion at the end. Thank you so much.
Thank you so much. Yeah, Amit, thank you, everyone.